we do the last process, adiabatic process. So adiabatic process, you're looking at thermodynamics. Q into gas is delta E of gas plus work done by gas. And in adiabatic process, the heat into the gas is zero. Okay, so no heat is exchanged between the gas and its surroundings. So Q is zero. So that means that the gas is going to do work, and the change in energy is going to also change. But if the gas is doing positive work, then the delta E is going to be negative, right? So if this is zero, delta E of gas plus work done by gas. So on the PV diagram, if the gas starts like, let's say here, and does some kind of work and goes to here, you know, so let's say something like this, it goes this way, so that it does positive work, right? Then that means the delta E of the gas has to be negative, you know, because it's going to be zero. So that means if the gas is expanding and doing work against its environment, it has to cool. If the process is adiabatic, because you're not putting heat in, when a gas expands, it's got to cool. If it's going the other way, if the process is going the other way, so that means the gas is doing negative work. So now it's being contracted adiabatically. If the work by the gas is negative, then the delta E of the gas has to be positive. That means it's got to be heating up, change. Its temperature has to change. So if we look up the adiabatic process, Google it. This is kind of good. What is an example of an adiabatic process? So it's kind of nice to see just regular examples of different processes in even nature. An example of an adiabatic process is the vertical flow of air in the atmosphere. The vertical flow. So you know how we say hot air rises, and when it rises, it cools. So that's the vertical flow of air. So it's saying air expands and cools as it rises. You see, so warm air rises. Why does warm air rise? There's a couple things that's happening, right? So warm air rises. So let's say you have warm air here. Warm air is rising because warm air tends to occupy a bigger volume, right? Than, let's say, the same mass of air that's warmer, because air is expanding, right? When it's warm, so in other words, the same mass of air that occupies a certain volume while it's cold, that same mass of air occupies a bigger volume when it's warmer. You see? So that means the density of warm air is slightly less dense than cold air. You see? So if the density of warm air is less dense than the density of cold air, you see? So therefore it starts to rise. When it starts to rise, it tends to cool, because that's where the colder air is, you see. So it tends to cool, so then what happens? What was I trying to do? Oh, it goes in this direction on the PV diagram. As it's going up, it's starting to push on its atmosphere. It goes like this. So the same warm pocket of air, as it's going up, it's pushing on its surrounding. So the warm air. So let's say the surrounding is just regular temperature air. Let's say you have, let's say this is your house, and you have like a fireplace here. So the fireplace is heating up the air on the bottom, right? And then the warm air starting to rise because it's less dense. Then it's starting to push on the regular temperature air, so it's starting to expand. So it's going this way on the PV diagram. So as you're sitting in front of the fireplace watching a TV show, you should try to visualize what's happening to this pocket of air, as it's rising. So then when it's going this way, what is it doing? It's doing positive work on the regular temperature air, you see? That means the delta E has to go down. So that means as it goes up, the temperature of this warm air starts to drop. So if the regular surrounding is, let's say, on a cold winter day, let's say it's like 6 Celsius. Well, hopefully the room is not that cold. Maybe it's 18 Celsius. But you turn on the fireplace because you want it to reach the 25. It's more comfortable, you see. So then the warm air starts out really warm near the fireplace. Let's say it's 30, right? And as it's starting to go, it's starting to drop, 25. And as it goes up, it expands more. It goes to, maybe it goes to already 18. The same temperature as your regular air. You see,
so as it's colder, it's 18 degrees Celsius, so the air has a bigger volume?
Yeah. So in other words, this is an adiabatic process. And there's no heat exchange. No heat is coming in from the surrounding, and no heat is escaping from here to here. Of course, because the surrounding is already colder, the heat would never come in from the surrounding. It would come from a hotter. In this case, since the surrounding is colder, the heat is not going to come in. But you're also not losing heat to the surrounding, you see. If it's adiabatic, truly adiabatic, you're also not losing heat to the surrounding. So in other words, it's almost like this pocket of air is acting as an enclosed surface with nothing, no heat exchange to the surrounding. They're saying that this could be modeled as an adiabatic process, even though it's not purely adiabatic, but it is kind of adiabatic because there's no heat exchange. So another example is when interstellar gas cloud expands or contracts. Adiabatic changes are usually accompanied by changes in temperature. The adiabatic process occurs without the transfer of heat or mass of a substance between the thermodynamic system and its surroundings. In the adiabatic process, energy is transferred to the surrounding only as work. See, so there's no exchange of energy as form of heat between the pocket of air or the gas and the surrounding. So then, of course, if it expands, we expect it to cool. So there should be, eventually what's gonna happen is, as the warm air rises, it cools, then it starts to sink. It might even be that, let's say this one reaches up there and goes even below the temperature of 18, right? So then what happens? Let's say it reaches 12 when it gets there. I'm just exaggerating. So when it gets to 12, then that's gonna be denser than the surrounding. Cold air is denser. Then it's gonna sink. And then you're gonna have, what do they call that? Convection of heat. That's called convection. When warm air rises and then turns cold, and then cold air sinks because it's denser. And then when the cold air sinks, then the fireplace warms that up, right? And then you get a nice convection going, like that. So if that pocket of air goes up and gets cooler than the surrounding, which it probably might, then it'll sink back and then it'll circulate, see, like that.
Could you explain the PV diagram again?
Oh, we're gonna develop that more.
Okay.
Yeah, right now.
Alright.
Okay, so then it says some chemical and physical processes occur so rapidly that they may be conveniently described by the term adiabatic, meaning that there is not enough time for the transfer of energy as heat to take place. So even though there might be slight transfer of energy, but events that are quick tend to also be called adiabatic, because if it's quick enough, then you don't have much time for transfer of energy, you see. That's what it's saying. Processes occur so rapidly. This is to be distinguished from the term adiabatic in the adiabatic theorem of quantum mechanics. Let's go on. Let's see. Okay, so now the next thing we want to do is to say, okay, how does the PV diagram of an adiabatic actually work? So what happens? PV is nRT. From the three processes that we've done so far, isobaric, the pressure has been constant. Isovolumic, volume has been constant. Isothermal, T has been constant, right? So is one of the three constant in this case? And the answer is no, because delta E is changing in adiabatic, so T is changing because delta E is changing, you see? Now, for work done by gas, that means already the volume of the gas is changing, so V can't be constant, you see? So if this is changing and this is changing, maybe pressure can be constant, you can argue. In other words, the PV diagram can look like this, can it? If this is changing and this is changing, see, it's doing work and the delta E is changing. It's cooling. Oh, but if you're gonna argue that the gas goes up, if it occupies a bigger volume, but the temperature changes. So in other words, this is increasing and this is dropping. In other words, mathematically, can the pressure be constant if the volume doubles and the temperature is halved? Or the pressure could stay constant. In other words, just simply from this argument, I can't argue that the pressure here has to be different than the pressure there. It can be the same mathematically. It depends how much the volume changes. If the volume doubles and the temperature is halved, then it can work. Remember, when I say temperature is halved, it has to be halved in the Kelvin scale, not on the Celsius. You see? So if the volume doubles and the temperature is halved, the pressure can't stay constant. But it's going to end up that in adiabatic, pressure can't stay constant, and the derivation of it takes some work. So to derive the adiabatic, we do like this. We say, so we want to basically, the next step is to derive how pressure changes as a volume in an adiabatic process. Okay, so what we're gonna do is we're gonna say, take the derivative of this, P dV plus V dP. Take the derivative of this times the derivative of that, plus that times the derivative of that, is equal to nR dt. Okay, and work by the gas And then from here, you have 0 is equal to what? If the heat is 0, what's the dE? E is NCV dt, right? E is N times the specific heat at constant volume dt, plus work by the gas is what? PdV. So literally you have two differential equations. You've got this one is the derivative of this guy, okay? And then this one is the first law of thermodynamics expressed in the differential form. So dE is equal to NCV dt. This is the definition of CV. Remember, CV is defined as 1 over the N dE dt at constant volume, right? So then that's going to be that. So then I'm going to combine these two, right? So let's see here. What do I do? Oh, okay. I'm going to take dt, solve for it. Yes, and then take the dt, solve for it, and substitute it into here. Let me see. Why did I solve for dt? Because if I want to know how the pressure changes as volume, I want to get rid of T as a variable. I want to get rid of T from the situation. So get rid of T by solving for dt, putting it in here. Then you have nR negative PdV over NCV. And then you're left with PdV over NCV, N cancels, N cancels. PdV plus VdP is equal to negative R P dV over CV. Right? Can I take this and combine it with that PdV? Right? So then I can say PdV, take this, put it on the left side, plus R over CV, PdV, plus, so I'm combining this with this, plus VdP is equal to 0. Then combine these two. PdV, 1 plus R over CV plus VdP is equal to 0. Okay? And what's left? PdV, CV plus R over CV plus VdP is equal to 0. Now, what's that equal to? We spent a whole hour on that concept the other day, the gamma factor, right? Remember Cp over Cv? The gamma factor in the gas. This is that factor popping up again from Monday. Cv plus R is Cp, divided by Cv is gamma. So then we have gamma times P dV plus VdP is 0. So in order for a process to be adiabatic, see, how do I know it's adiabatic? Because I set delta E plus PdV equal to 0. See, I set the Q equal to 0. So then that's how I know it's adiabatic. That means the adiabatic processes depends on the gamma factor. You see, so now I want to develop how does the pressure change versus volume. So the next thing to do is to take this to the other side. Gamma PdV is equal to negative VdP. And then take the P down here and the V down here. So gamma dV over V, negative dP over P. And then take the integral of that. Then you're left with ln of gamma ln of V is equal to negative ln of P plus some constant. So then raise both sides to the power E. Right? So in other words, my goal is to come up with this equation. This is the final thing. PV to the gamma is constant for an adiabatic process, right? We're almost there. So you take E to the this, and then of course this goes to the power, right? And then E cancels the ln, and this goes here, and then E cancels the ln here, so we're left with what? So the gamma goes up to the top, you get V to the gamma, and then E to this, so the negative goes to the power, -1. So then you have 1 over P, and then E to the constant is just another constant. And then you can cross multiply. PV to the gamma is a constant. Okay, for an adiabatic gas. So in other words, as the volume is going up, the pressure is dropping. That's what that is saying. Because if you put this here, V to the gamma, right? That means as the volume is getting bigger, pressure is dropping. Now, the relationship in the isothermal process, in isothermal, what was it, the relationship? PV is nRT, and this is a constant in isothermal. So pressure is constant over a volume. So this one depends on if the gas is monatomic or diatomic. So if let's say it's a monatomic gas and gamma is 1.67, right? So then the pressure would be equal to what? Constant over V to the 1.67, right? So if the volume doubles in an isothermal process, the pressure is halved, okay? So graphically that means this. If the volume starts here, the pressure starts here. If the volume doubles, I should say like this. The volume doubles, pressure is halved. So isothermal would look like this. Right? But adiabatic is going to look like what? If the volume doubles, what happens to the pressure? Constant over 2 to the 1.67. Right? 2 to the 1.67, that's going to be what? .314. Okay, so in other words, the pressure should drop to 30% of its value. So it's going to look more like here, kind of. So adiabatic would look like this. So if the same gas is increasing its volume, doubling its volume isothermally, its pressure maintains its pressure more. You know, even though the pressure drops, you're maintaining. Why? Because you're actually putting heat in. In an isothermal, you're actually putting heat in. Q into gas is what? Delta E of gas plus the work done by the gas. So isothermal, here's what happens. Delta E is 0. So the reason in an isothermal, the reason the gas is expanding is because you're putting heat into the gas, right? And when you're putting heat in, that's allowing the gas to do work. And when the volume is increasing, the reason that its temperature is not dropping is because you're putting heat into the gas. And so even though the pressure is dropping, it's not dropping as much as it should drop. You see? Because you're putting heat into the gas and the gas molecules are vibrating quicker. You see? In an adiabatic, it's expanding just because, depends what reason. In the case of the warm air, it's expanding because it's less dense, right? And you're not putting any heat in. So not only is it gonna cool, it's not gonna maintain its pressure also. So the pressure is gonna drop more, you see? That's if it's monatomic. If it's a triatomic, maybe it's gonna look like this. Triatomic will look more closer to the, triatomic will look like that. The pressure won't drop as much because gamma for triatomic is 1.28. So it's gonna look more like the isothermal, but it's still gonna drop more. It's still gonna drop more than an isothermal, you see? So this is monatomic, this is polyatomic, and then this is diatomic, nice and colorful. This is diatomic. D, P is polyatomic, D is diatomic, M is monatomic. So that's what they mean kind of in this kind of a graph. So what are they trying to show? They're saying that if you expand adiabatically, you're going from one isothermal graph into another isothermal graph. You see? So in other words, I could imagine an isothermal graph like this, and then draw another isothermal graph like that. So you're basically changing from one isotherm to another isotherm. So from your initial temperature, you're dropping to your final temperature. So you're changing isothermal graphs when you're going adiabatically. See, from here down to here. So the compression stroke in a gasoline engine can be used as an example of adiabatic compression. So in a minute we're going to start chapter 20. So we'll see that heat engines, depending on the cycle they use, they could use the adiabatic process. So gasoline engines use an adiabatic process. See, like that. Okay, this is the derivation that I just did. Nice. Oh, except mine was a bit nicer. Okay. Okay, so maybe what we could do is, now that we've got the adiabatic defined, we've got the gamma. Now let's go to chapter 20, because we're gonna see different kinds of engines and the cycles they run through. And then several of them will use an adiabatic process. Okay, so let's go to chapter 20 now.